a friend and colleague, Dr. Quan Guo. And Quan is a geomechanics advisor at QuantumPro Incorporated. And previously, he was with SLB, MI Swaco, Advantech, and TerraTech. And his experience includes nanoparticle tracer flow monitoring and analysis, perforating and hydraulic fracturing lab testing and modeling, drilling fluids, and wellbore strengthening, cuttings, and produced water reinjection, among other things. He has 14 patents, and he's co-authored or authored over 80 technical papers. He holds, as we heard, he holds a PhD in mechanical engineering from Northwestern University. A pleasure today to introduce Dr. Quan Guo.
Okay, thank you, John. Appreciate it for the introduction. And good morning, good afternoon, good evening, wherever you are. And this talk is really based on a recent paper that I presented at the Unconventional Resources Conference in Houston earlier this month, which was held, unfortunately, at the same time as the Rock Mechanics Symposium in Santa Fe. So when John asked me to give this talk at your monthly meetings, I readily agreed, thinking that many of you may not have seen it. If you have seen it, and I added more materials because this talk has 45 to 50 45 minutes limit versus only 20 minutes allowed at the Unconventional Resources Conference. So I hope you'll get something out of it too. So here is the outline of my presentation. Let me move my thing out to my view. And so I will start with a background of our nanoparticle tracer technology, including example how to use the tracers for stage level flow mapping and the values added. Then the motivation and the concept of using the tracer embedded charges for perforation level flow mapping over cluster efficiency. After this, I will discuss the laboratory tests and the results to confirm that the tracers in the charges can withstand the charge detonation. Then the field tests and the results to validate the tracer detectability at the field condition, and also to assess how long the tracer will remain detectable. In other words, how long we can use it for cluster level flow mapping. Finally, conclusions and before questions and discussions. As I said earlier, these presentations really based on a recent paper shown here. So I'd like to thank my co-authors, particularly Wallace, Hendrick, and True Oil. They trust us early on and provide the opportunities to test this technology in their wells. Because as you know, a technology like this, if we don't put it into a well, it is just a concept. So we are really very appreciative. Here is a very brief background and the values of the nanoparticle tracer. QuantumPro has developed approximately 220 unique nanoparticle tracers for high-resolution flow mapping. These tracers have a particle size between 0.1 and 1 micron, so extremely small. A density very similar to oil or water, resulting in excellent suspension in oil or water. We also have tracers for gas, but for this talk, I will focus on these tracers. The tracers have a very high temperature stability, up to 2000 degrees Fahrenheit. It is non-radioactive, non-hazardous, safe, and inert. So entirely new class of tracer, different from radioactive or chemical tracers. It is compatible to oil and water. So basically one tracer for both. It is easy to deploy and cost-effective, non-intrusive to well operations. For example, in the case of multi-stage hydraulic filtering, all we do is to use a handheld pump to dose about 10 parts per million of the tracers at the mixer with the propellant. So no risk to mess up the well operations. And the tracer detection, testing, and analysis is quick and accurate. All we need is about 1 gallon of fluids from the wellhead. So no logging, no other things required. All you need is the wellhead production fluids. And the tracer detection is based on energy dispersive X-ray fluorescence, basically on the subatomic structure of the tracers. So as you can see, it's an entirely new tracer, new class, and with so many tracers available, you can trace every stage of a multilateral well, multi-stage lateral well, whether it's 50, 80, 100. So since it was introduced in 2019, it was growing very fast. Here is a list of the customers and the projects from like a small independent to super majors, mostly for the long horizontal wells with many stages of fractures, and also the enhanced geothermal system wells because of its high temperature stability. So next, I will show example on how to use the tracers for stage level flow mapping and what we can do with the stage level flow monitoring results when we have the production versus time for every stage before I get to the cluster level. So this example is from a recent SP paper shown here. It is a Eagle Ford well from Repsol. It has 63 stages. We traced every stage with a single tracer by pumping the tracer with the propellant. So when the well turned back into production, we get about 1 gallon of fluids periodically. And from the tracer recovery results, we can get the stage level production. Here I show the stage level, relative stage level production contribution for all the 63 stages on different days. And when we know the production of the well, we can convert it to the stage level production. And also I showed here it is the average, basically 100 divided by 63 for every stage. So you can see some stages above, some stages below. Plotted here is the accumulative or stage level production in barrels for a selective few stages. And if I plot all the stages, you won't be able to see much. So as you can see, versus the time, as a time production history, stage level production history results, as you can see, some stages are way below the average, which is dashed line, which is obtained by the well production divided by the 63. Some stages are way above the average. Some stages initially about average, but then declined very quickly. Some stages initially is average and then increased later on. And we also have some stages that is below average initially, but then keep going, picked up later on. So the point is that using the nanoparticle tracer, we can monitor the stage level production versus the time for every stage. So basically it's a 4D PLT if you wish. The stage level production monitoring results versus time allows us to do a history match, for example, and a diagnostic evaluation at the stage level. If a stage performs poorly, we can do some analysis to see if it's due to poor reservoir quality or poor fracture well in connectivity. In other words, ineffective well completion, or both. I should also point out maybe that another important objective of this monitoring project was to evaluate the impact of hydraulic fractures on the fault and casing integrity. So for this well, there is a major fault in this region. And when they complete the well, they noticed that this could cause the fault activation and casing failure. So one of the objectives they asked is how much contributions from the production contributions from the few stages near the fault. If we don't have much, we can just skip it, avoid the risk. So from this analysis, I taught them there is a very little production from the few stages around the fault. They can skip them safely to avoid the risk of casing failure. So anyway, and this slide shows is a give example how to use the stage level production versus time to do some analysis to get the completion and reservoir quality diagnostic. And it's based on very simple method. I'm sure you can do much better, particularly if you have a reservoir or a production simulator to do the production history match. So what I plotted here, it is the stage level cumulative production, 30-day and 6 months for every stage. So basically it's a replot of this figure. So I come here to get the 30-day production, stage level production, and 6 months stage level production I get. So, and also plotted here is the average stage level production, 30-day production, and 6 month production. Basically is the well 30-day production divided by 63, 6 months well production divided by 63. So from this plot, you can see some stages are above average, some stages are below average. Then I use the 30-day over short-term production as epoxy for the completion quality. In other words, how well the fractures are connected to the well. I use the 6 months or long-term production as epoxy for the reservoir quality. Again, like I said, you can do better than this, but this is what I did in a very simple way. So as you can see, for these few stages, this region, we have about average completion quality, but we have above the average reservoir quality. For these few stages, we have both good completion quality and good reservoir quality. So basically, this is a very simple analysis, and like I said, you can do better. But this is just for illustration. So the point is, these 2 slides, this example, give you example of stage level flow mapping and diagnostic, and also illustrated the value from well level to stage level production monitoring. The reason we can do this is that we have many tracers, so we can trace every stage, whether the well has 60 over 70 or 80 stages. So then from the large number of the tracer really provide a method for an interventionist 4D production mapping monitoring technique. Also, we can see from this, the stage level production monitoring gives us a better view than just a well level production monitoring. If I could use analogy from the well level to the stage level, it's like from a blurry black and white TV view to a color TV view with more pixels. Now, we want to get the high definition, high resolution digital view at the cluster level. So I will discuss next how we do this using the tracer embedded charges. Here I show a concept of using the tracer embedded charges for the perforation level flow mapping or cluster level flow monitoring. So as you know, a charge consists of the liner, the explosive, and a steel case. The charge liner is made from a powder metal blend by pressing into a mold. So the tracer is added into the blend before the pressing, before making the liner. So basically, the tracer, the liners contain the tracers in the pore of the liner. Is a porous material there. And because the tracer is nanoparticles, mostly the tracers are in the pore. When we detonate the charge, the explosive generates a very high pressure, and the liner collapsed to form a jet of solid particles, the liner particles and the nanoparticles. And that jet can be, 10 kilometers per second, enough energy to punch a hole in the casing and into the formation. So the jet during the charge detonation carries the tracer into the perforation tunnel and the rock formation. And the charges with the tracers look and perform exactly the same as the charges without a tracer. And there is no difference in gun loading or wireline or TCP operations. No additional procedure are created from this. And there is no additional personnel is required to do that. So we don't have a person or engineer on the well to deploy the tracer. So this does have many advantages. So the concept is quite straightforward. The question is, will it work? And that's why we needed to answer several key questions to prove it. Among them are, will the tracer embedded the charge withstand the charge detonation? Secondly, how much tracer we can put in the charge without affecting the charge performance? Because again, we don't want to make the charge perform poorly. So these two questions will be answered from laboratory test. Then can the tracer be detected after a very large hydraulic friction treatment involving hundreds of thousands of gallons of water, hundreds of thousands of pounds of sand, and especially when we have very little amount of tracer in each charge. So if yes, how long the tracer will remain detectable? So these are the key questions we'll be answering from the field test. So here I show the laboratory test set up according to the API RP90B standards for the charge testing. Here I show a gun, a perforation gun inside a well bore, and these are the schematics of test setup. Here we have the charge. The gap between this gap is simulate the charge in gun clearance. There is a gap between the charge and the gun carrier. And then the scallop thickness, which is simulated the gun thickness, scallop thickness. Then the water gap between these two plates, which is the water gap between the gun and the casing. Then the casing plate here, and then the rock or cement core. In our test, we use cement core. So basically, this is what the standard says, and to simulate a gun in a well bore. So we have done many tests with on different charges with a different level of tracers in the charge liners, from 1% to all the way to 10%. We found that no significant effect on the casing entrance hole size, with up to 5% of the tracer in the charge liner. I think one of the reasons for this is that the nanoparticles occupied the core of the liner. We do find some effects on the depth of penetration from just a few percent to 20%. But more significantly, testing on the samples collected from the perforated core confirmed that the tracers embedded the charge liners withstood the charge detonation. So this is very significant because other materials couldn't survive the charge detonation. Here I show a couple examples of the casing entrance hole. And here is the tracer recovery concentration in parts per billion for charges with 1%, 2%, and 5% of the charge liner materials. So with this result, like I said, we have to put it into a well to demonstrate the technology. So with these results, we went to field tests, and 2 field tests were performed. The first one is on a high temperature, high pressure well in North Dakota to validate the detectability of the tracers and also different deployed methods I'll elaborate next. And the second test involved 2 wells to assess, like I said, how long the tracer will remain detectable and the consistency, repeatability of the tracer detection. Here are the well trajectory of the first well. Actually, that involved a lot of faults there. Here is the well trajectory of the second well, second test. Yeah. So this is the first field test well design, the test design. This, again, like I said, it is a high temperature, high pressure well in the Wilmington Basin, and the bottom hole temperature is about 300 degrees Fahrenheit, and it has 40 stages with this much of gallons of water and this much of pounds of sand per stage, and 8 clusters per stage, and each cluster was perforated with 4 charges. So stage 12 and 13 were selected for the test. So in stage 12, we have gun 1. We have the 4 charges in gun 1 contained about 1 grams of tracer 1 embedded in the charge liners. Gun 2 to gun 8, the 28 charges contained about 6 grams of tracers embedded in the charge liners. Like I said early on, with these little tracers, and we are not, before the test, we are not certain whether we'll detect anything after this much of water and sand injection. So we also put vials of tracers in the gun loading carrier and loading tube, and tracer number 3, the total amount of tracer 3 in all the 8 guns contained about 500 grams. So we know for certain from our previous experience, we should detect this level of tracer at this much. So for stage 13, all the guns we loaded with regular charges. These charges contained no tracer in the charge liners. So what we did was to put a 3D printed tracer infused ring in front of the charge. So this way we can put a little bit more tracers per charge without affecting the charge performance. So for gun 1, we have about 5 grams of tracer. And in gun 2 to 8, we have about 34 grams of tracer. And as you can see, this was the first test. We tried to design our test to cover a wide range of tracer levels, from 1 gram to 5 gram to 30 grams. So these are the retrieved spent gun, and for these for some of the clusters. So this slide shows the tracer recovery results in parts per billion, and after this much of water and sand injection per stage, after the well was shut in for 2.5 months at 300 degrees Fahrenheit, because this 2 stage was completed on August 1, and we didn't turn back, that well wasn't turned back for production until October 14. We got our sample. The first sample was on October 21 at 9 a.m. So it is 1 week after the well was produced at about, I didn't list it here, about 1,200 barrels per day. And so we, this is when we see this result, we were quite excited. Actually, Wallace was, comments was, I never thought we'll see anything, because after 2.5 months at this, and we know with, this is a very, it's kind of high temperature for this. So even for at the 1 gram tracer level, we see some, we see recovery, albeit very low, but certainly for the 5 grams tracers in the cluster, we saw, they are sufficient for robust detection because of this kind of a low level. So that's why in the second test, we designed many just clusters with just 1 grams of tracer per cluster. So with these, we were very excited, and True Oil immediately gave us the second opportunity to test these on another field test. For this test, and 2 wells are involved, and they were zipper fracked in October last year with 41 stages with this much of water and this much of pounds of sand per stage. Again, it is 8 clusters per stage, and each cluster was perforated with a 4 charge, same as the first one. And 6 stages were selected for this test, as shown here. And for this test, it was exclusively for charge embedded with a tracer in the liners. So it is all the tracers are embedded in the charge liners. And for the stage 14, the gun 1 to forward have loaded with the 16 charges embedded with a total amount of tracer embedded is about 3.7 grams. And the gun 5 to 8 was basically the repeated test of this one with another unique tracer. Then we have 5 repeated 1 gun only, with each gun loaded with 4 charges with a unique tracer embedded in the charge liners. And the total amount for the 4 charges is a tracer is at 0.9 grams. Then we have 3 repeat the test, all the 8 guns were loaded with the same tracer and the 32 charges. And for these 8 guns had contained about 7.4 grams of unique tracer. I should point out that originally stage 39 of this well was selected, but it was changed to stage 31 of this well. It's very easy to, operationally very easy, just like allocate the 8 gun for these stages, save it for this one. That is how it happened. And the reason is that this stage 31 for this well was landed outside the reservoir formation. So we wanted to know if any productions from this out of zone stage. So that is the purpose for this change, and that is the purpose for monitoring this stage. So anyway, as you can see, we designed our test for the following objectives: more data points, and the repeatability, consistency, and the longevity, how long of the tracer will remain to be detected of the tracer detection. So these are the purpose for this second field test. So for these 2 wells, the flowback started November 27, and with the initial rate about 1,300 barrels per day. And 2 batches of samples were obtained. The first one from December 15 to 17. The second batch from January 7 to 15. So these here shows the tracer recovery results from the first batch of sample. And so again, in parts per billion. As can be seen from the results, we have good tracer recovery for all the cases, including the 1 gram cases. And the results are consistent and repeatable. And all the 1 gram cases has a similar results, and 3.7 gram similar results, and 7.4 similar results. And we see that more tracers give greater recovery. And so you can compare the 7.4 and all the 80 guns versus just 4 guns, 4 clusters versus 1 clusters, right? The results also confirm the production from this out of zone stage for this well. Remember, we changed our test plan to include this stage for this purpose only. And also you see that the 1 gram tracers lasted at least 3 weeks after the well was put on production, right? So this is basically like 3 weeks that started on the 27th, and this is the 17th of December. So then the question is how long the tracer will remain detectable. So that is the reason we get the second batch of sample from January 7 to 15. And this is about 50 days or 7 weeks after the well was put on production. And we see all the 7.4 gram tracer cases, they showed a good tracer recovery, very strong. And also the 3.7 gram tracer cases showed a very good tracer recovery as well. For the 1 gram tracers, some of the stages we didn't see anything, but although most of them still showed a very strong recovery. Remember, one of the objectives is how long we can monitor the cluster level production. So when a tracer doesn't, this cluster doesn't have any tracer recovery, it could be two things. One is the no production from this cluster, or the reservoir depleted. Second, it could be due to that the tracers in this cluster had completely depleted, so no tracer recovery. Consequently, even there is a production. But I think the most likely case is this stage, this cluster, there no production from this cluster. The reason is that if you compare these, even from the very beginning, this cluster was a very poor production from this cluster, poor production from this cluster compared to other clusters. So as time goes on and the reservoir depleted and the production from this cluster basically shut off, no production. But since one of the objectives when we see the tracer detection, we wanted to know is that how to relate that to production. So we are conservative. From this result, we said this for 1 gram tracer, for 3 weeks production, it will be there will be tracer production if there is a production from that cluster. So that is the point I wanted to make. But also you see on the 3.7, it lasted at least 7 weeks. So below 7 weeks, we know for sure about 4 grams tracer will last 7 weeks. So I believe this is a monitoring technique using the tracer embedded charge is a powerful enabler. And we can use it for other applications. I list a couple here. I'm sure there are more. For example, and this one is for unconventional, long unconventional well. We wanted, for example, if we want to know which perforation strategy is better, up and down or left and right. Let's say we have 50 stages and we have 8 clusters and we have 4 perfs per cluster. So I will have, we'll have 1,600 perfs. And if we load the perf, we use the exact same charge for these, but there was half of the charge with tracer A embedded, half with tracer B embedded. So we can look like a tracer A, and then tracer B, tracer A to the down, tracer B to the right, or we have shifted this one to the up, and this one, the whole gun is to the left, right, then down and right. So the point is, with these many tracers, and we can, these many charts, we basically eliminated the variables from the reservoir inhomogeneity, the reservoir variation. So that way, all we get is the charge orientation effect. And so, there is a second example, very similar to a charge A and a charge B. We can evaluate which one is a better charge for the specific well or reservoir. So I see a time running up a little bit, so I'm going to conclude my talk. First, a couple conclusions on the on the tracer itself. As I showed, the nanoparticle tracers are entirely new class tracers, right? So we can use it for high temperature and also the unique large number of tracers and high temperature stability gives many options and no other tracers can. So specific to the cluster level of monitoring using the tracer embedded charges, and the lab and field test confirmed that the nanoparticle tracers embedded in the charges remain detectable for weeks after production. More specifically, just 1 gram of tracer lasted at least 3 weeks production. 4 grams of tracer lasted at least 7 weeks of production. So this gives a method for perforation level or cluster level flow monitoring and diagnostic. And it can also be used for offshores. I mean, particularly for offshores because of no additional personnel is required for enhanced geothermal wells because of its high temperature stability, and in addition to the conventional and unconventional resources wells. And so with that, I will give control back to John and for questions and discussions. Thank you.
Thank you, Quan. I mean, very clear presentation, and maybe we're talking about a revolutionary technology here. It's just outstanding. We do have a couple of presentations, or excuse me, a couple of questions. The first is from Evgenia, and the question is, do you have any idea why the production per stage on slide 5 is roughly periodic? Now, that's maybe outside of the box, but maybe you have some thoughts on that.
Let me go back to well, I mean, that is probably, when you say periodic, that means some stages, like up, some stages down, and it's like this kind of, assume that what it means, the periodic. This is one of the objective for the monitoring, because I assume, this is the good ones, probably related, because of the geological difference, right? Because it's a long horizontal well, there is a good reservoir or good, even if it's not a very good reservoir, but it's even, just, average reservoir for some of the zones, I mean, the period, the region. But if the rock mechanism property is different, even you use exactly same completion design, they create a different completion quality. So that is my inputs on this. Again, like, probably the operators have much more data, logging and formation. They can do an analysis to see why.
Okay, thank you. And then the next question is from Brian. And Brian observes that, wow, there's an overwhelming number of combinations that you could manufacture with more than 200 tracers, different charges, sizes, et cetera, et cetera. How do you see implementing this in practice? How are you going to choose
okay, yeah.
this?
Yeah, I mean, yes, there are so many combinations, and so that gives us such, so many flexibilities. For example, now we got two wells. There are wells we, like we monitor maybe using 100 tracers, because we want to not just watch one tracer per stage. We have a tracer in the front, tracer in the middle, tracer in the near the wellbore. We flow back and see, give more granularity. In terms of cluster level, or like put the tracer in the charges, we, after the unconventional resource conference, people already talk about, okay, I have like 60 stages of well, and 3 stages I wanted to monitor every cluster. And so for each stage has 10 clusters. If I wanted to monitor every cluster for these stages, so we are talking about, see, 30 unique tracers, right? And then plus that. So this is many, many combinations. I don't know if that answer the question, but yeah.
Maybe,
But
Brian,
again, sorry.
Sorry, Quan, go ahead. I apologize.
If it's a people can contact me, if I didn't answer your question. Go ahead. Sorry, yeah.
Well, Brian's follow-up question was that he suspected that the 3D printed ring that would fit multiple charges would have some real advantages.
Yes, that is a perfectly comment, because another one is for the charge. If you do anything alternation to the charge, there is a very strict regulatory process and go through. And with the rings, that will give you a lot of flexibility. And like Brian was saying, and you can fit it to multiple charges. Yes.
And so Jorge's question is that even though tracers can be detected, how much of the embedded tracer can survive to make mass balance calculations? Did you see anything from your API testing of how much would actually survive?
Yeah, no, yeah, that is, we could do that. Yes, we could do that, but it's, once we get that, and we just went to the field test. But this is exactly how much, whether it's the 50% survived or 80% survived. So the reason, reason is we have to, for every cluster, we embedded the same amount of tracer. So it is, let's say, 1 gram tracer per cluster, and it's only 50, there is only, 0.5 survived, but it's by looking the relative strength recovery, we get the production allocation per cluster on the cluster efficiency. It's a good question, and practically we didn't go that deep.
So Eddie has a question, and he said, instead of adding to perf charges, can you add unique nanotracers to the slurry per stage? And later stages may contain remnant tracers, et cetera, but each stage will have its own unique tracer to isolate it. And I think, go ahead.
Yeah, yes, I mean, the question is yes, and that's what we did. The first example I showed you, it is basically we add a unique tracer for the every stage, yes.
Yeah, and Jorge has another question, and in terms of some of the differences between cluster performance and even stage performance, what was there background logging that would indicate geologic differences that you could recognize?
Proper like the first question regarding the periodic, like when we do the diagnostic, we see that this one has a good reservoir quality, and we give that results to to Repsol. We didn't have their logging data, but they said, oh, this is roughly is what we see, and we don't see anything wrong. So that, yeah. So
Okay.
yes.
So
Yes.
the answer is yes, that
Yes.
it can be confirmed with logging.
Mhm.
And Joe France, Joe wants to understand a little bit more about how you estimate the production per cluster. Let's see. So you produce, Joe says you produce the particles to the surface and they're detected during well production. How do you estimate the production per cluster or stage?
Okay. So it is so it's basically weighted by the recovery strength. So if I use an analogy like this, I have two buckets of water, and I put a bucket, tracer in A in bucket A, tracer B in bucket B, and they have exactly the same concentration. In other words, 1 unit of a tracer is correspond to 1 unit of the same amount of water. So if you give me a mixture, the production fluids give me a mixture of these two, and I did a test, I find 2 units of tracer A, 1 unit of tracer B, I will know the fluids, the produced fluids has 2 parts of production from A, 1 from B. If I know the wellhead, produce 300 barrels, and I will know 200 from A, 100 from B. That's how this. So same with the cluster. I mean, yeah.
Okay. Well, we've sort of reached the end of our time, and I would like to thank Quan very much for a very, very enlightening and stimulating presentation. And I'd like to thank everybody for joining in. So thanks all, and we'll see you next time.
Thank you.
Thanks, Quan.
Thank you.